So before we get too far into this, let's remind ourselves what our original function was. The original function was x squared minus 2x plus 4 all over x minus 2. And our derivative function here, our derivative function was x squared minus 4x in the distributed version, x minus 2 quantity squared. Okay, so what do I need to do here? I need to find the second derivative, analyze the second derivative so I can determine intervals of concave up, concave down, and any inflection points. So for the second derivative, f double prime of x, we're going to use the quotient rule. The quotient rule is the low, which would be x minus 2 quantity squared, times the derivative of the high, while the derivative of x squared minus 4x would be a 2x minus 4, minus the high, which is x squared minus 4x, times the derivative of the low, using the chain rule, that would be 2, drop the power, x minus 2, keep the inside just the same to the power minus 1, times the derivative of the inside, while the derivative of x minus 2 is simply 1. All of this is over the bottom, which is x minus 2 squared, that quantity squared. Okay, so let's do some work here. I want to be a little careful here. What I notice is that if I distribute this, on the left I have, well, there's a couple ways I can do this. So I see this as x minus 2 squared and a 2x minus 4. So what I'm noticing is I also have a 2x minus 4 on the right-hand side. And then what can I do with that x squared minus 4x? So let's look at this and see what I can do. If I factor both of the parts, so I'm going to factor out a 2 from the first, I'd have a 2, I'd have an x minus 2 squared, and I'd also have that x minus 2 if I factored that out. On the second one, I can factor out an x, so that'd be an x times an x minus 4. I also have the 2, and I also have an x minus 2. All of this is over x minus 2 raised to the 4th power. So the only reason I'm doing this is I'm trying to see what common factors can I take out. So in this left factor, I see that there's a 2 and an x minus 2, and in the right factor, I also see that there's a 2 and an x minus 2. Even though technically x minus 2 squared times x minus 2 is x minus 2 cubed, I'm not going to look at it. I'm just going to take out the x minus 2, and I'm also going to take out the 2 from both sides. So let's see what happens when I factor those out. I'd have a 2 and I'd have an x minus 2. So what happens to the first term, if I take away the 2 and the x minus 2, there would still be an x minus 2 squared left over. On the second term, if I take away the 2 and I took away the x minus 2, there would be the minus x and then the x minus 4 left over. On bottom, we have the x minus 2 raised to the 4th power. Let's do some cleaning up here. I do notice that we can factor and simplify one of the factors of x minus 2. So that'd be x minus 2 cubed on bottom and a 1 on top. So on top, I'm left with 2 times, and let's go ahead and distribute out the top, x minus 2 squared, foiling it. I'd have x squared minus 2x, which would be minus 4x. Then I'd have a plus 4. I'm going to distribute the negative x through, so I'd have negative x times x is minus x squared, and then the negative x times the negative 4 is actually plus 4x. When I do that, and I have x minus 2 cubed on the bottom left over, when I do that, I notice that my x squareds are canceling and my 4x's are canceling. So the only thing that I have left on top for my second derivative, I just see the number 8. And then on bottom, I still see my x minus 2 quantity cubed. So that's my second derivative, nice and simple, an 8 over x minus 2 quantity cubed. Again, I need to know, when is the second derivative equal to 0? Well, that's when the numerator equals 0. 8 cannot equal 0, so that never happens. My second derivative is never equal to 0. When's my second derivative undefined? Well, my second derivative would be undefined when the denominator equals 0, so that's x minus 2 quantity cubed equals 0. Cube root both sides, and I'd have x minus 2 equals 0. Add 2 to both sides, and I'd have x equals 2. Again, this we know is our vertical asymptote. It is not in the domain of the original function, so it cannot be an inflection point. So I already know that there's no inflection points because there's no points to break it up other than at the vertical asymptote. But I still need to determine my concavity, so I still need to consider my real number line. I still need to break it up at x equals 2. I know my second derivative at that point is undefined, and I know for my function at that point I have a vertical asymptote. I look at the first interval, which would be negative infinity to 2, and the second interval, which would be 2 to infinity. I need to plug these into the second derivative. Again, the second derivative here was 8 over x minus 2 quantity cubed. I need some number less than 2, so how about 0? Some number bigger than 2, how about 10? I plug them in. Notice my numerator is 8, which is always positive no matter what I plug in. If I plug in a 0, I'd have 0 minus 2 cubed, which would be negative. A positive over a negative is negative. So for the whole first interval, my second derivative is negative. When I plug in 10, I have positive on top. 10 minus 2 is 8. Cubed is positive. A positive over a positive is positive. So that entire second interval needs to be positive. Again, when my second derivative is negative, my function has to be concave down. And when my second derivative is positive, my function has to be concave up. I would like to say that x equals 2 is where a inflection point occurs, but again, that point is not in the domain of the original function. That cannot be an inflection point. All that is a vertical asymptote. So let's answer for intervals of concave up. That's where the second derivative was positive. That's on the interval 2 to infinity. Whereas at concave down, that's where the second derivative is negative. That's on the interval negative infinity to 2. Again, inflection points, there were none in this case because we had no points in the domain where we changed concavity. So what do we do at this point? Put it all together. Let's go back to step 1 and see what we got. We had no x-intercepts to work with, but we did have a y-intercept of the point 0, negative 2. Again, my y-scale here I really don't care about too much, so I'm just going to put a dot there. We do have a vertical asymptote at x equals 2. So I'm just going to drop that vertical line down all the way to x equals 2, and I'm going to write vertical asymptote below it because that's what it was. Horizontal asymptote, we have none. We did know that there was an oblique asymptote, but we don't care about that. That's perfectly fine. Okay. So no horizontal asymptotes, no x-intercepts. We can't get any of that information. So this is really all we could take from the first part. Now let's go back to our second part, part B, and let's look at the first derivative. What did the first derivative tell us? Well, the first derivative did tell us that we did have a point of 0, negative 2, which was our y-intercept. We know this point is a maximum. What else did it tell us? Well, it told us that the point 4, 6, so maybe something like right there-ish, has to be a minimum, which seems pretty interesting, but that's what it is. Okay. That was our maximums or our minimums, and now we need our intervals of increasing and decreasing. So if you remember, we got to break this up everywhere that's broken up on the number line for part B. So go back to part B and essentially copy and paste that number line directly below this. So where was that first one broken up? It was broken up at x equals 0, which we know is a maximum, at x equals 2, which we know was a vertical asymptote, and at x equals 4, which we know was a minimum. What was our derivative? Our derivative was positive. Here, let me write f prime of x here. Our derivative was positive for the whole first interval, negative for the next one, negative for the next one, and then positive for the last one is what we ended up with. So now that we've written all our maximums, minimums, and our signs of our derivative, let's move on to the second derivative. The second derivative didn't give us any inflection points to cover, so all we can do is show the sign of it on the intervals below. Broke it up at 2, that's where we already have it broken up at, so let's look at our sign. Anywhere before 2 was negative, so in both of these intervals my second derivative has to be, sorry, let me move that up a little bit. My second derivative has to be negative, and anywhere after x equals 2, my second derivative has to be positive. This gives me enough information to work with the shape of the graph, so I can determine the shape of my function f of x. If my second derivative is negative, that means I'm concave down or a frown. My first derivative is positive, so I have to be increasing, so that means I have to be the left half of a frown. In the next interval, my second derivative is negative, so again I'm a frown, but my first derivative is negative, so I have to be decreasing. That would be the right half of a frown. In the next interval, my second derivative is positive, which means it's concave up, or a smiley face. My first derivative is negative, so that means it's decreasing, so that would have to be the left half of a smiley face. My last interval, I have a second derivative that's positive, so it's a smiley face. My first derivative is positive, so I have to be increasing, so that would be the right half of a smiley face. So what do? I come to this and I look at this, and again, there is an oblique asymptote, but I don't care that you make it look like there's an oblique asymptote. In other words, and rather than approaching a horizontal line, it approaches a diagonal line, but I truly do not care about that at this point in time. What I care about is the general shape. So I need to be the left half of a frown, and I need to touch the point 0, -2. So that would be something like that right there. Then from 0, -2, I need to approach my vertical asymptote at x equals 2. And it looks like I have to do the right half of a frown, so it looks like I approach it in a downward direction, approaching negative infinity. I come to the right of x equals 2. I need to approach the asymptote x equals 2, so I'm going to do that from the high side. And then I need to use the left half of a smiley to connect it to the point 46. From the point 46 on, I realize that I have to use the right half of a smiley going back up, so it would look something along those lines right there. So there's my graph of my function. I have the accurate shape in every single interval. I have the important points labeled for that graph. I can now go on Desmos and verify that I've done everything correct. Again, you cannot use Desmos to get the correct answer, but certainly if you're not taking a test, you can use Desmos to verify that you have the proper answer. And that's what we have right here.